Hello, welcome to Visionarics, our podcast where you can have real and simple conversations with us about various tools and technologies. I'm gRPC, and
I'm Cassandra. In this podcast, we dive into exciting discussions about simple and deep technical topics in the world of DevOps and cloud. You can find the full transcript of this episode on our website visionarics.tech to follow along with us. Stay tuned and enjoy the adventures in the world of technology.
hello, I am gRPC. I am a modern communication framework for distributed systems. Who are you?
Hello to you, gRPC. I am Cassandra. I am a distributed database with high scalability. Can you tell more about yourself and your role in today's world?
Of course. In 2024, many people think network and communication issues are no longer a challenge. But the truth is, as distributed systems get more complex, new challenges have appeared.
That's interesting. Can you explain more? What challenges still exist?
Yes, of course. While basic protocols like TCP/IP have improved a lot, today we face systems with hundreds or thousands of microservices. In such an environment, managing communications, ensuring reliability, and maintaining efficiency are still challenging. For example, 1. Scalability. When thousands of services are exchanging data, managing optimal communications without getting involved in network details is a big challenge.
Oh, don't talk to me about scalability. I am the master of horizontal scalability. I can manage billions of rows of data across thousands of nodes without breaking a sweat. But I must admit, managing communications between all these nodes sometimes reminds me of the telephone game in nursery school.
Wow. Okay. 2. Fault tolerance. In large systems, errors are unavoidable. Managing these errors and ensuring the system continues to work has its own complexities.
That's my line. I protect data by replicating it across multiple nodes, like a worried mother sending her child to a party and giving 1,000 instructions. Even if half of my nodes fail, I'm still standing. I think in my past life, I must have been a cat with 9 lives.
3. Latency. As the number of services increases, managing delay in communications becomes more important.
Latency, my old enemy. I try to minimize latency using a ring structure and smart data distribution algorithms. But sometimes, when data travels from one end of the world to the other, I feel like I'm watching a marathon race.
Security. As systems grow, ensuring security at all communication points becomes more complex.
Security? I'm like a medieval castle with moats and high walls. From data encryption to complex authentication, I cover everything. But sometimes, managing encryption keys in a distributed system reminds me of trying to keep cats in a bag.
Heterogeneous environments. Today, systems often use a mix of languages and platforms, which makes communications more complex.
Oh, I'm a real polyglot. With drivers in different languages, I can talk to any system, from Java to Python and Node.js. Sometimes I feel like a United Nations interpreter trying to manage an international conference. I just hope I never get lost in translation.
I am designed to solve these challenges: scalability, fault tolerance, latency, security, and heterogeneous environments. Using advanced features of HTTP2 and my own special features, I try to hide these complexities from developers.
This is very interesting. I'm curious about HTTP2. Can you explain more about the HTTP2 features you use and how they help solve these challenges?
Of course, HTTP2 has several key features that I deeply benefit from. 1. Multiplexing. This feature allows me to send multiple requests and responses over a single TCP connection. In practice, this means I can manage thousands of requests simultaneously without additional overhead. This feature greatly reduces latency and increases throughput. 2. Header compression. Using the HPAC algorithm, I can effectively compress HTTP headers. This not only reduces the volume of transferred data, but also helps improve security by preventing compression-based attacks. 3. Stream prioritization. This allows me to specify the relative importance of different streams. In complex systems, this means optimal use of network and processing resources. 4. Binary protocol. Unlike HTTP 1.1, which was text-based, HTTP 2 uses a binary protocol. This makes processing faster and reduces errors from parsing. 5. Server push. Although I don't use this directly, this feature has great potential for improving performance in specific scenarios. Now, let me talk a bit about my roots. I am actually a new generation of RPC, remote procedure call. The main idea of RPC is that calling a function on another computer should be as simple as calling a local function, local procedure call. I have taken this concept and optimized it for the modern world of microservices and distributed systems. By combining these HTTP features and RPC concepts, I have been able to create a communication framework that is not only fast and efficient, but also very simple and usable for developers.
Wow, that was really comprehensive and deep. I can see how these features can be effective in solving communication challenges in distributed systems. Especially multiplexing and binary protocol seem to have a big impact on reducing latency and increasing throughput. In my world, we focus more on optimizing reading and writing data, but I see we have similar challenges. The concept of RPC and the effort to simplify communications in distributed systems is very appealing to me.
Now that I've talked about myself, I want to know more about you, Cassandra. What was missing in the world that led to your creation?
Well, my story started with Facebook. They were facing big challenges in scalability and availability. The world needed a database that could handle huge volumes of data and still be always available.
Facebook? Like the site Mark Zuckerberg made in his Harvard dorm room? It's interesting how it grew from a simple idea in a dorm room to such a tech giant.
Have you seen the social network?
No, I haven't. But when you mentioned Facebook, I quickly checked IMDb and did a bit of internet search. It's really interesting to see where Facebook came from and how big it is now.
Wow, your speed is really amazing. Well, as I said, I was created to solve the CAP theorem problem.
Just like when Zuckerberg realized he needed to expand his site to cover more users.
Exactly. I was designed to create a good balance between consistency, availability, and partition tolerance.
This is like the challenge Facebook faced when expanding to other universities, right? But I still don't fully understand linear scalability. Can you explain more?
Of course, linear scalability means that with each new node added, my capacity and performance increase linearly.
Sorry, I still don't quite understand. Can you give a more concrete example?
Think of a restaurant kitchen. If one chef can prepare 100 meals in an hour, linear scalability means that by adding another chef, the capacity increases to 200 meals per hour.
Oh, so it's like adding a new server to Facebook. But how does this work in the real world of DevOps?
Exactly. In the DevOps world, imagine you have a service that processes 1,000 transactions per second. With linear scalability, if you add a new server, you can now process 2,000 transactions per second.
Oh, so it's like when Facebook added new servers to cover more users? But is it always this simple?
No, it's not always this simple. There are challenges like coordination between nodes and managing distributed data, but I'm designed to minimize these challenges.
I understand better now. So you actually help DevOps engineers expand their systems without worrying about scalability limits?
Exactly. And this is very crucial in today's world, where data volume and traffic are rapidly increasing.
It's really impressive. It seems we could collaborate on many projects.
Exactly. Imagine what powerful systems we could create by combining your communication power with my storage and scalability abilities.
Let's talk about a real-time data analysis platform. I work in the data transfer layer and use advanced operating system mechanisms to optimize network communications. For example, I use an asynchronous I/O system that directly communicates with the OS kernel. This allows me to manage thousands of connections simultaneously without needing to create separate threads for each connection. In fact, I use an internal event loop that continuously checks the status of all connections using system calls like epoll in Linux or kq in BSD.
I act as a distributed storage system that runs directly on the operating system. When I say I am in the storage and data management layer, I mean I'm positioned between the application layer and the file system layer. In fact, I use low-level system calls like read, write, and a map to interact directly with disk and memory. I use the kernel's file system, but I have my own methods for managing and organizing data. From a network stack perspective, I'm in the application layer and use TCP/IP for communications between nodes. However, I've implemented my own protocol on top of TCP that's optimized for data exchange between Cassandra nodes. Regarding memory management, I use a complex combination of heap memory and memory-mapped files. My memory tables are in the heap, while for quick access to sorted string tables, I use memory-mapped files that directly interact with the kernel's virtual memory system. This complex structure allows me to provide high performance in read and write operations, while maintaining scalability and fault tolerance.
Interesting. For data transfer, I use an encoding system called protocol buffers that directly interacts with low-level OS layers. This encoding system converts data into a compressed binary format that can be directly transferred over the network. In fact, I use a ring buffer that holds the encoded data and transfers it as soon as the OS kernel is ready for sending. This mechanism allows me to continue working even when the network is slow or unstable.
I also use a complex algorithm called consistent hashing for distributing data between different nodes. This algorithm creates a circular hash space and places each node at several points on this circle. When data comes in, the hash of its key is calculated, and the data is sent to the node responsible for that section of the hash space. This system allows me to maintain data distribution with minimal change, even when nodes are added or removed.
Thank you for listening to Visionarix. You can find more technical and practical discussions on our website, visionarix.tech.
Thank you for listening to Visionarix. You can find more technical and practical discussions on our website, visionarix.tech.
Next time, we'll be talking about Git. Goodbye for now.
Goodbye.